Let us have a brief overview of the Gaussian distribution. It is sometimes also called as the normal distribution as well. In order to discuss this, let us start or begin by writing the expression for the distribution. Fx is given as 1 upon sigma times square root of 2 pi. This sigma is a constant which we will discuss further in detail. E raised to minus x minus mu bracket squared divided by 2 sigma squared. So mu and sigma are constants. We have already defined what are mu and sigma in the previous lectures. Mu is nothing but the mean or average value of x, of course the arithmetic mean, and sigma is the standard deviation which measures the spread of fx, the amount of spread of fx from the mean value mu. So this is an exponential curve. As we can see, it involves e raised to minus of some quantity squared. So first thing, that it is an exponentially decreasing curve. Obviously the maximum value is going to be at x equal to mu, since in that case e raised to 0 would be equal to 1. And it has to be, since it involves x bracket squared, for positive as well as negative values of x, it has to be symmetric curve. So the curve look like this, and we can allocate the values of sigma plus 2 sigma and so on accordingly. Of course these values correspond to certain specific conditions. So this corresponds to f of mu. Note that the probability is maximum, so this is p, which is f of x. So f of x, or the probability, is maximum at the mean value mu. This is the obvious case. This curve is called as a bell-shaped curve. As the name suggests, the curve appears to be shaped like a bell structure. Accordingly, the cumulative distribution can also be defined as f of x being equal to 1 upon sigma root 2 pi. The same thing. Now we have to integrate starting from the lower bound, and lower bound corresponds to minus infinity to a certain value of x of our interest, x. This term e raised to minus t minus mu bracket squared by 2 sigma squared dt. Correct. Now note that this previous discussion regarding the binomial distribution involved discrete functions. So distribution of binomial case was a discrete function, but this Gaussian distribution is, as can be seen, a continuous distribution. Continuous distribution. Since this is symmetric, we can also understand that if we are asked to find out f of mu, we need to cover half of the curve starting from minus infinity to mu. Since half of the curve is covered, half of the probability is covered, since the curve is exactly symmetric about mu. So a capital F of mu is just going to be half of the total probability, that is 1 by 2. This is an important result. Now this is positions of sigma. So if somebody asks the area, so whenever we integrate, we are calculating the area under the curve. So if somebody asks what is the area from minus sigma to plus sigma, that can be found out by calculating the value of f of x accordingly, from integrating from minus sigma to plus sigma, and that is covering up to that 68% of the area. That is, the probability corresponding to a region from minus sigma to plus sigma gives 68% of the area, of the total area. If sorry, accordingly, if we extend this up to minus 2 sigma to plus 2 sigma, the area covered, so this is minus sigma to plus sigma. Now the next stage is minus 2 sigma to plus 2 sigma. The corresponding area covered rises very sharply and it becomes 95% or just 0.95 if we talk in terms of absolute values. Accordingly, if we cover from minus 3 sigma to plus 3 sigma region, so again we extend this curve to minus 3 sigma to plus 3 sigma, the corresponding area covered is almost 99.7%. So almost practically the entire area is covered over this particular region. So nothing much is left beyond this region, as can be understood from this percentage. So this drops very sharply. The exponential curve drops very sharply as we move away from the mean value mu. That is the essence of this discussion. We can approximate the binomial distribution by a Gaussian distribution in some special cases. As we can see, binomial distribution is just f of x given by c n x, p raised to x, q raised to n minus x. Right. Now, if the n value is large, that is the number of trials is very large, as well as the product of n into p is very large, this can be approximated by calculating the values of sigma and mu. So sigma and mu can be easily found out for this value f of x. Sigma in that case appears to be square root of n times p times q, and mu appears to be simply n times p. So if we use these values of sigma and mu into the expression for the Gaussian distribution, we effectively approximate the binomial distribution by the Gaussian distribution. So in that case, f of x is going to be 1 upon square root of 2 pi npq. We are replacing sigma by square root of npq into e raised to x minus np bracket squared upon 2 npq. Npq is sigma squared and mu is np. So this is an approximation of a binomial distribution by a Gaussian type of function. Of course, this is true only when both n and the value of n into p are large. We will consider an example in order to understand this structure. Suppose there is a coin. As we know that there are only two possible events, either a head or a tail. Now if a coin is tossed 100 times, and we are asked to find out the probability that we get exactly 52 heads. So P corresponding to heads, of course 52 heads, is just 1 by 2, and Q, which is corresponding to the tails, which is 1 by 2. So 52 is the value of x here and 100 is the value of n here. So value corresponding to q, which is n minus x, which is 100 minus 52, is just 48. So we can write it as f of x equal to c nx. So c 100 comma 52 p raised to x, which is 1 by 2 raised to 52, q raised to n minus x, which is 1 by 2 raised to 48. So this is a much complicated number and we need computer to solve this. And if we solve this using a computer, we get value of f of x to be equal to 0.0735. Right. So this value of the probability is calculated using the binomial distribution, because the problem contains the case of tossing a coin which has only two possible outcomes, head and tail. Now we note here that this n value is typically very large. 100 is not a small number. And again, n into p, which is 100 into 1 by 2, which is 50, is also very large comparatively. So since both n and n into n into p are large, we can approximate this by a Gaussian distribution. In that case, first we need to calculate mu, which is just n into p, which is 100 into 1 by 2, which is 50. And then we need to calculate sigma, which is square root of np cube, square root of 100 into half, which is 10 by 2. Square root of 100 is 10, 2 into 2 4, square root of 4 is 2, which is 5. So mu is 50 and sigma is 5. And the Gaussian distribution, as we know, is f of x is 1 upon 2 root pi sigma, e raised to minus x minus mu bracket squared upon 2 sigma squared. So let us just substitute for mu and sigma and x. Our x value in this case is 52, because we are asked to find out the probability corresponding to 52 heads, exactly 52 heads. So f of 52 would be 1 upon root 2 pi, sigma value is 50, right? Not, yes, 50, no, sorry, sigma value is 5. E raised to minus 52 minus mu value is 50, bracket squared, upon 2 into sigma squared. The sigma is 5, so 5 squared is 25. Now again, this, in order to solve this, we need to have a calculator or at least a computer, and we get f of x, or x in this case is 52, so f of 52 will be equal to 0.0736, right? So we can just recall that the value of f was 0.0735 when we used the formula for binomial distribution, and in this case, when we are using the Gaussian type of distribution formula, we are getting the value 0.0736. So we should note that these two values quite match very well if obviously value of n and value of n into p are large enough. This is how we approximate a Gaussian distribution or a binomial distribution by a Gaussian distribution. Thank you.